both the Turfino and the MSMAs have single suppliers in the world. Not feel very comfortable with it currently.
Okay, here's a very interesting chart that compares the different materials. This force over deformation. First is the piezos. They are on a very high force already, but deform only very little. Better already are the magnetostrictive materials. Again, higher forces, and on a more or less equal level of forces are shape memory alloys, while they produce larger deformation, fluctuation, strain. So going in this direction, there's energy density effect. Okay, and of course, we would like to get into this region here. You see the hydraulic actuators are already here, but of course there are all these negative effects associated with hydraulics. So replacement in this region would be very interesting. The EIPs, by the way, in the muscle, they are here. Also an interesting thing that while producing low forces, you've got a very large deformation. Okay. If you think of the body muscle, that's a very good thing, because you don't have to apply much force to get really something moved. Okay, here's something we heard already by Ian today. The micro-electromechanical systems, or easier MEMS. MEMS is a very fancy word, by the way. MEMS could be everything that's micro and systems, but we refer here to MEMS because that's on a very low micro scale, so really low scales, and all that's done with an integrated circuit. And you can see an example here. There's sensors and there's also actuators on this low scale level, all put onto wafers by MEMS fabrication techniques, as Ian has shown this morning. So you fabricate the system to give you the component and then the overall system by packaging everything together. And you even can get sensors and actuators at the same time on the same wafer, on the same chip, to get then an intelligent actuator. So an actuating or an active element which can sense and actuate at the same time. An interesting example here is some micro flaps which just come out of the surface and move with a certain frequency which can be activated, which could be interesting, for example, for noise control. And there's an accelerometer. It's about the case Ian has shown. Okay. The issue associated with MEMS is that there are commercial applications, very large volumes of that, but not for aerospace applications at the moment. And we think that for aerospace, these low costs are unlikely to be achieved, just because of the amount of devices needed and the patch size. There have been demonstrations of actuators, new MEMS actuators. Small scale devices have been developed. They can be distributed anywhere with multiple actuators. For example, for boundary layer manipulation. Very interesting. But of course, they've got all the constraints associated with these tiny and delicate elements that damage tolerant. If we think putting them into an engine inlet. Cost and maintainability is an issue which needs to be explored. But it's all related to the business case here. So we need to have an application with large volumes. So not only for aerospace, but also for other industries. Now here's another principle of actuation, which is called plasma actuator. The principle is to have a voltage potential by putting into a material two electrodes, so here and here. One electrode is buried, so it's important. And what happens is that this voltage potential ionizes the air, and then the electric field here in between gives a force, and this force gives us a momentum transfer towards the outer medium, for example, the flow. And here's a nice example. What's happening here? This is called electron avalanche. You've got in the first time step ions which form just by the potential by the electric field between those two electrodes, one outside and one buried. These ions then accelerate towards the electron, towards the electrode. Electrons, of course, accelerate, and they ionize the material here. Okay. While accelerating, they ionize outer material. And that's an avalanche process. So every electron ionizes more atoms, and therefore new electrons are free to ionize more, and it's like a real avalanche. And this process goes back and forth between those changing current, and the force is always in this direction because this electrode is buried. So this electrode here can absorb and release electrons, and this can't because it's just shielded. Okay, so this is plasma actuation.
Is that a AC force?
DC.
It's a DC.
So
you can switch it on and off. Yeah, so typical experiments don't run with constant voltage applied, but the same applies. We've seen yesterday. It can be done in pulses. I'll show an example.
Okay. Good. So here's a very easy example to show how it could be applied. Plasma actuator. So you put this actuator into the airfoil, into the material, and activate it, and therefore transfer a force and momentum towards the flow. Here it's a boundary layer which is detached, and you energize this boundary layer by the plasma, and therefore reattach boundary layer. So this could be an example for an airfoil. Another interesting and emerging technology is the combustion actuator. It produces a jet, basically a jet coming out of a volume here. The jet is pulsed, and it's really here a tiny combustion chamber. So you have got some reactive material, reactive gas going into that. You have an ignition, combustion, and then a pulse combustion in the equivalent jet. And that's design is very simple, while you get very large impulse out of it. And you could think of large arrays now, which produce tiny jets and could then manipulate boundary layers or flows. And that's, for example, a technique which could be a MEMS, could be integrated into a MEMS. by the way, I've got this example here. So it's very small. You've got this slot here sitting, and all this is a thickness of only 5 millimeters. And well, you've got a combustion going on inside. Okay, now here's my summary. You saw that enhanced actuation can be very productive, but is at the same time very challenging. We need to respect the limitations we have in the gas turbine. Again, same thing as for sensors. We have got an aggressive environment. For actuation, we have to consider which application we are heading for, which active control technology we want to realize. Of course, there's much development needed. For example, in certification, supply chain requirements. And the baseline is that there are technologies which are ready on a laboratory level, laboratory scale, that have turned out to be proven technologies on a very early stage. And they've got to be driven towards application. And that's the point. Drive the emerging technologies towards real products, and hence they raise the technology readiness level. And therefore we need to have not only the push but also the pull from industry. So the demand getting these technologies into the product. Okay, so are there any other comments or questions on that part?
General, maybe a hard question also. Which one of all of these is the furthest along commercially?
Hard to answer. From my side, I would say piezos are very far already. They are used in automotive industry. Like BMW, for example, uses these stacks of piezos in their engines for fuel injection. However, they've got constraints for aerospace, especially gas turbine applications. Another thing which is available is shape memory noise. So we have got these devices. We just need to apply them. I think for these two technologies, the step is very the step is very small, which has to be taken. But today you can only apply that into the colder region, for example, in the nozzle, in the bypass, in the inlet, not in the gas turbine itself.
Okay. This is one of the drawbacks of memory always. They operate to about 150 degrees. If you want to push them to 300-400, I mean, they some research, but it's very...
I will show an example afterwards. They are used also potentially for clearance control. Could be used there.
But we talk about
again, you have to separate the actuator from the flow, just to avoid the high temperature problems.
So there are examples.
Right.
But you have to do some development for high temperature applications, or you have to get to consider taking these elements out of the hot environment.
Now it's time for a coffee. Now we have fresh coffee. Yeah. This will take